All right, so we're continuing our treatment of chapter 18, which was mostly about things like enolates and carbonyls. Lately, what we ended on was conjugate addition. Conjugate addition to alpha beta unsaturated carbonyls and alpha beta unsaturated carbonyls, and that's also what we're calling enones. Okay, and we showed a couple examples. I'll repeat one of them briefly. Amines. Amines, of course, we have an example. So this is it's an alpha beta unsaturated ketone, right? Alpha beta, unsaturated means there's the alkene there. And let's just, as an example, throw in dimethylamine. So it's a secondary amine. Secondary amine, right? It's an amine with two things on it. For each of these, there's always an H2O step also. So it's going to be the amine is going to attack the beta position, and then water. You need the second step to kind of finish the mechanism. So the end product will be the ketone. It'll be like that. Yeah. Okay, and what's the mechanism of this? The mechanism is that the nitrogen and its lone pair attack the beta and make an enolate. Okay? And that's we talked about that last time and why that happens. And now you have an enolate. Okay? And how do you finish this off? It's just really the oxygen grabs a proton, H plus, and a base or water or something takes a proton. You could almost call it a PT, and if you did that, that's fine. I understand what you mean, because you're transferring a proton to the alpha position, and you're removing a proton from the nitrogen. So if you just summarize that and say PT, I'm totally cool with that. Proton transfer. Okay, so that was amines. Second example, we're leading to the really cool example of conjugate addition, but let's do one more one more example. Cyanide or CN minus. This is also an example of a 1,4 addition. There's the important lone pair is on carbon. Okay, so let's just show an example. Okay, so another simple alpha beta unsaturated ketone. All right, let's do. I think what the book usually uses is HCN. Okay, and the product is that. So it's going to be another conjugate addition. Conjugate addition. What's the other name I give it? It's called conjugate addition, or we talked about this last time. But if I do a numbering from like position 1, 2, 3, 1,4, then I also call it a 1,4 addition. Conjugate addition or 1,4 addition, right? Okay, anyway, what do you think the mechanism is? How does this work? Well, the HCN is an acid. We know ketones like to get protons from acids, and just do that. Okay, the ketone grabs a proton. Like that. Now I just to do this kind of rapidly, just have the cyanide attack. Where's it going to attack? Well, it looks like we know where the product is. It's at the beta position. So just have the cyanide's attacks. Actually, the end result here is not quite the product. It's close. I'm sorry. It's, what is it? Now we have CN, and we have this thing. And what's that called? What's that called? Of course, it looks like an enol, right? And it is an enol. Let's fix my camera a bit. Yeah. Okay, so yeah, it's an enol. It's an enol of a ketone. And this just tautomerizes. Tautomerize. We learned this mechanism earlier. This is essentially a proton transfer also, where the O proton gets transferred to the alpha position. So we learned that in the beginning of chapter 18. Okay, so yes, cyanides do 1,4 additions. Cyanides do 1,4 additions. Amines do 1,4 additions. Now, number 10. So this is maybe the most important kind of common conjugate addition. This is 1,2 versus 1,4 addition of organometallic reagents. 1,2 or 1,4 addition of organometallic reagents. What are what organometallic reagents we focused on a lot? Generally RMGBr, right? Grignards. What's the other one? The other metal that we've kind of seen a lot. Lithium. R-lithium, yeah? Okay, so these are the common ones we've seen 1,000 times since organic 1. Now the new one is going to be R2CuLi. R2CuLi. It's called a cuprate, and it's going to be different. Quick summary: these are going to give 1,2 addition. What do you think the cuprate's going to give? The cuprate's going to give 1,4 addition. Okay, let's see examples now. Alright, so let's do a Grignard. So this is plain old organic 1 chemistry, Grignard. And, this could be orphenylithium, pH lithium, right? They do the same thing here. That's the thing. Grignards and organolithiums in general do the kind of same thing as we say up here. Grignards and organolithiums are going to do 1,2 addition. What did 1,2 addition mean? It means that we're directly attacking the ketone. We're directly attacking the ketone. And so So this is kind of like normal old organic 1 chemistry. That's the product, right? And this is a 1,2 addition. So the Grignard attacks the ketone. What's the mechanism for that? Well, remember, we can kind of abbreviate the Grignard as pH ... minus, in quotes. It's kind of like a carbanion, so it's, or you could say, right, it's kind of like this also. It's like a benzene with ... negative MgBr plus, okay? Carbon negative, metal plus. Anyway, so we can just abbreviate this as phenyl minus. And what's the mechanism? It just attacks. So this is a plain old Grignard, right? And then the O minus grabs a proton, right? The O minus grabs a proton. And there's the alkene there still. Don't forget the alkene. Okay, cool. So this is a 1,2 addition. Now what is the cuprate going to do? What do we say cuprate's going to do? The cuprate is going to be a 1,4 addition. Okay, a 1,4 addition. So let's show an example. And we'll talk a little bit more about cuprates in a second. A big thing is that they have 2 parts. So it's like, it's not going to be phenyl copper lithium, it's phenyl 2 copper lithium. So there's 2 phenols on a copper, and there's a lithium. Okay? And add a water step. And what do we say? Is it a 1,2 addition or 1,4 addition? Grignards are 1,2. Cuprates are 1,4, so they're just going to attack at the 4 position. End result, puts the phenyl right there, or you could, put the phenyl down. The location of it doesn't really matter. Okay, let's just abbreviate the cuprate as phenyl ... minus also. Okay. So this phenyl ... minus is different than this phenyl ... minus. The reason, the reactivity of the copper species is different than a Grignard, and without going into all the technical detail of it, they love to attack 1,4. These love to attack 1,2. So now all we do is have the Grignard attack. Sorry, the cuprate. Make an enolate. That's easy, right? Phenyl ... minus attacks the carbon. Electrons move to make an enolate, and what does that make? That with a phenyl now here. I'll draw out the phenyl. Cool so far? And now, just grab a proton from water. So the enolate swings down, and the double bond grabs a proton, and you are done. This is the product of the cuprate. Okay? So the cuprates are a different kind of organometallic reagent. And they attack 1,4. So the phenyl cuprate, which is basically a special phenyl ... minus, attacks the carbon, makes an enolate, and then the enolate grabs a proton from water, and you're done. Okay. Obvious question then is, how how do we make a cuprate? How do you make a cuprate? Well, how do you make a Grignard? I mean, those are easy, right? Phenyl bromide. How do I make phenyl magnesium bromide? A Grignard. You take the bromide and you throw in magnesium. Maybe dry THF. Or some dry solvent. Okay? Phenyl bromide, magnesium, and that's a Grignard. How do you make organolithium? Whoa. How do you do that? Well, you add lithium and dry THF or something. Those are easy. We learned that in Organic 1, right? How to make a Grignard, how to make an organolithium. How do we make a cuprate now? And you might just think, oh, throw in some copper, but it's a little more complicated, just a little bit. You throw in 2 lithiums. Well, I'm gonna say lithium. Well, actually, let's go back to the top one. Yeah, the organolithium. You actually write the letter 2, the number 2. Okay, because there are 2 lithiums, and you get a lithium bromide out. There's also in the byproduct. It's not that important, but when you're making an organolithium, it's actually 2 lithiums. Okay, well, we're going to do the same thing here. 2 lithiums to make phenylithium and lithium bromide. So we have the stoichiometry of that, yeah? And then we're going to now take the two phenylithiums, and we're going to react that with copper iodide. Copper iodide. And this does everything. So this creates phenyl to copper lithium. Okay, and we can call this, and also that makes lithium iodide also. The byproducts are not a big deal really. You know, that's kind of gen chem type stuff, stoichiometry, balancing. The big thing is understanding the structure of this and its reactivity. Phenyl to copper lithium. What is the structure of this? You know, what do you think the structure is? You have 2 phenols, a copper, and a lithium. It's probably phenyl, copper, phenyl, copper, phenyl. Phenyl, copper, phenyl, yeah? What's the charge of lithium usually? It's positive. And this is negative. So this is the structure. It's phenyl, copper, phenyl. Phenyl, copper, phenyl. Negative on the copper, positive on the lithium. Okay, and a name for it might be diphenyl cuprate. Diphenyl cuprate. Or phenyl cuprate. The big thing is the word cuprate. Cuprate suggests copper. Okay, diphenyl cuprate. Okay, cool. So let's show another example. Another example. Okay, so how about this one? What if we take that'll be our starting material. And what if we react this copper lithium? What is that? Well, it looks like it's 3 carbons, copper lithium, like propyl cuprate. Propyl cuprate. Propyl cuprate. Propyl cuprate. It's got a 3 carbon piece, copper lithium. What if we react with ethyl bromide as our second step? So we can imagine this can be, we can actually try, because remember what does the cuprate do? The cuprate attacks, creates an enolate, and enolates are nucleophile, right? What if we have that enolate and give it an ethyl bromide? Well, guess what's going to happen? You're going to add the propyl to the beta position, make an enolate, and then attach the ethyl to the alpha position. This will be the final product. Okay, let's see how that works. Let's see how that works. Okay, so to draw my my propyl as a nucleophile, I could just circle the bond and have it attack. Right? The bond, the carbon-copper bond, can be an attack. Alternatively, I could say something like this, you know. It's 3 carbons dot dot negative, and I could have one of those the carbon attack as well. Okay, what does that give us? What does that give us? Well, the cuprate and the carbon, that last carbon there, the 3rd carbon, attacked. Let's zoom in on that so you can see it, how I drew that. Okay. So I just circled the bond, right? The bond attacked the carbon, and that makes a what? An enolate, right? So, yeah. So now we have our 3 carbon piece, and what else do we have? An enolate. And enolate. And what do you think the ethyl bromide does now? Because we have ethyl bromide. So now the enolate can attack the ethyl bromide. So I'll just have the enolate attack, and that puts the ethyl group at the alpha position, right? Cool, so that's nice. All right, what's another thing we could do to this now, that final product? Maybe a Grignard. What would a Grignard do to this? A Grignard would attack the ketone, so how about let's do that. Throw that in pH MgBr. Okay? Step 1, step 2, H2O. What does a Grignard do to a ketone? The Grignard is going to do what to the ketone? Attack the ketone, the product. Look at that. We just did 3 things in rapid succession. 3 things in rapid succession. We added the cuprate to the beta carbon as a 1,4 addition to create an enolate. Enolate attacked ethyl bromide to put an ethyl group at the alpha carbon. So propyl's on the beta carbon, ethyl's on the alpha carbon. Then we added a Grignard to the ketone to make a tertiary alcohol. It's pretty cool. We did 3 things in rapid succession. Okay? Okay. So kind of remember that as a strategy. We can add a cuprate, add a ethyl bromide, or another alkyl halide, add a nucleophile, add an electrophile, and then add another nucleophile. We're going to do that in a second, so keep that strategy in your mind right now, okay? Okay, so since alpha, beta, unsaturated ketones are so useful, as it looks like, they're very useful, how can we make them? How to make. So I showed you this already, and I'm going to see if you remember how we did this. So how do we make them? Like, how do I convert this ketone into the corresponding alpha beta unsaturated ketone? We learned how to do that. And how did we do that? It's a two-step process. First, you got to put, introduce a leaving group at the alpha position, and then you have to kick off the leaving group from the beta position. So the way we learned that, this is a two-step process, right? It's a two steps. How do we attach a leaving group to the alpha position, and what leaving group is it? Well, it was bromine. It was Br2HO, is acetic acid, right? Bromine and acetic acid. That was early in this chapter, so you might want to review that. It's electrophilic bromination of a ketone. So we did the mechanism and everything. It's essentially you form an enol of the ketone, so that the acid causes enolization of the ketone, and then the enol is a nucleophile, and the nucleophile attacks bromine, kicks it off. Okay, and now you got the Br right there, yeah. And then how do we kick off the Br? Like an elimination reaction from organic 1 goes pyridine, PYR. So we did this, I think it was last lecture. We showed how to do this. Pyridine, of course, is like a benzene with a nitrogen in it, lone pair. It's a mild base, and all it does is it takes this proton off. Cool. So now that's how you make this. So now we know all these cool things you can do with this, like what? Like a cuprate. You add cuprates to those things, right? Okay. So let's make a synthesis problem now, using this and some of our new stuff. Example, synthesis. Okay, so how about okay, we have a ketone. Let's add 3 carbons there. Alright, there we go. It's a ketone. And let's just imagine, think of a product. I'm just making that up. Okay. Boy, that looks scary. Doesn't that look scary? That we did, like, we attached 3 things. What are the 3 things and what are the positions? Right. We attached an isopropyl group where it looks like where the ketone is. We attached a methyl group where it looks like the alpha position is. And we attached a ethyl group that looks maybe where the beta position is. So this is like where the ketone is, alpha, beta. Okay, so using everything we just learned, this is actually not that hard. The big thing is this we can envision this being done by a cuprate. The ethyl can be done by a cuprate, and then that makes an enolate, which we can trap with a methyl. And then we can attach this guy with a Grignard. Okay, so I'm going to do this in the forward direction just to expedite. What's the first thing we got to do though? Because this is not useful. This cannot be we can't just attach these three things. First thing we got to do is make the double bond, right? Like we just learned, right? Okay, and so let's do that. Let's first turn this into an alpha beta unsaturated ketone. How do we do that? Okay, how do we do that? Well, we just learned how. We want to convert the ketone into an alpha beta unsaturated ketone. It's bromine and acid and pyridine. One sec. Yeah, so bromine and acid will brominate the alpha position, right? Bromine and acid brominates the alpha position. Pyridine takes off the beta hydrogen, and that gives us the alpha beta unsaturated ketone. Now all we got to do is throw in our cuprate. So we're combining the last like 5 minutes. You know, I can throw in a cuprate. First I'm going to do the cuprate. What's the cuprate? Oh, it's going to be ethyl cuprate. So it's going to be copper lithium. Ethyl cuprate is going to attach the ethyl group to the beta carbon. And then that'll make an enolate. And what are we going to attach? That'll be the alpha thing, methyl. So maybe methyl iodide, CH3I. Cool. Okay, what does that give us? Methyl and ethyl. So that installed the ethyl at the beta carbon, methyl at the alpha carbon. Now what do we have to do? Attach the isopropyl group to the ketone. How do we do that? Last thing we do, attach that isopropyl thing at the ketone. How do we do that? It's a Grignard. So now it's isopropyl MgBr. Step 1. What's the step 2 of a Grignard? Water. So we just did 3 carbon-carbon bond forming reactions, kind of in sequence. The first thing we had to do is make the alpha beta unsaturated ketone. First you make the alpha beta unsaturated ketone, Br2 acetic acid, pyridine. Then we did the cuprate followed by methyl iodide. Cuprate attacked, makes an enolate, and then the enolate attacks methyl iodide. So now we have our ethyl and our methyl. And then we do our Grignard attack. Isopropyl Grignard attacks the ketone, followed by protonation, and makes the product. So that was a cool example of like combining like 3 different kinds of CC bond forming reactions, right? Very cool, I think. Okay. Okay, I'll have you guys do one synthesis problem for fun. Synthesis. Fun. Isn't this fun? So it's a 5-member ring ketone, and I'll say, make me try to do that. Okay, that should be a pretty straightforward example, and it illustrates all 3 kinds of CC bond forming reactions. Cuprate, alkyl halide from the enolate, and then a Grignard. See if you can do that. Okay. Number 11. Now we're going to do conjugate addition. Of enolate anions. What does that mean? Conjugate addition of enolate anions. What could that possibly mean? What's an enolate anion? It's something like this. There we go. That's an enolate anion, like from acetone, as an example. So acetone loses a proton, a base takes the proton, the alpha proton, and now you have an enolate anion. All right, so that's what an enolate anion is. This is going to have a name, a person's name. It's called a Michael reaction. A Michael reaction. Okay. Okay. And there's actually two versions and two names, and we're going to see them both. So how about I'm going to say there's two. There's the Michael reaction, and there's also called the, this is the easy one. We have the Michael reaction, we have the Robinson annulation. The Robinson annulation. Okay, and the Robinson is going to be essentially a Michael plus additional stuff. Okay, so I'll go through them both, obviously. We're going to have the Michael, which is kind of going to be the sort of the simple idea, and then the Robinson is going to be a Michael plus more stuff, a couple more steps. Okay, so let's first talk about the easy one, the Michael reaction. What is it? It's a conjugate addition of an enolate anion. So let's show the simple Michael. Let's do the Michael first. Michael reaction. It's really a 1,4 addition of an enolate anion. A 1,4 addition of an enolate anion. Here's the simplest example in the world of this. I got a ketone, and I got an alpha beta unsaturated ketone. Okay. This thing, it usually gets attacked, right? The right side thing gets attacked. It's an electrophile, right? And we're going to give it a name. We're going to call it the MA, not abbreviated after myself, but for Michael acceptor. This is the Michael acceptor, MA, Michael acceptor. And this thing is going to be the nucleophile. It's going to attack, and so it's going to be called the what? Maybe the MD. Okay, I like to identify those two things, the Michael donor, the Michael acceptor. Okay, and the reagent we're going to use for a bunch of these reactions is NaOET. It's a base, strong base, and maybe some ethanol. We're going to see that over and over, so get used to it. NaOET is the common base we're going to use for the Michael and also the Robinson when we get to the Robinson in a few minutes. Okay, so we're going to do the Michael, then we'll do the Robinson. The product of this is going to look like that. You can imagine it just it's sort of the attachment of the left thing and the right thing, and it just makes this long thing. And we're going to give this a name, this type of product, the product of a Michael. It looks like if I number my carbons, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. A good name for the product of a Michael is a 1,5-dicarbonyl. A 1,5-dicarbonyl, okay? So the product of a Michael reaction is going to be a 1,5-dicarbonyl. Okay. So let's do the mechanism. Base. So what is the base going to do to the Michael donor, the ketone? Well, as we've learned several times this chapter, bases take the proton off and do what to the ketone? What's a name for what we're doing? We're making the enolate. Okay, and what's the enolate? No, the enolate is a nucleophile or electrophile? It's a nucleophile. It's a nuke. Okay, and what's the electrophile? The Michael acceptor is the electrophile. I'll redraw that down here. Abbreviate it for now, pH. Okay. So what's the nucleophile going to do? And what do we learn about these things? Is they can be attacked. And for the most part, things attack the conjugate addition, the 1,4 addition, just like a cuprate. Some things attack the ketone, but a lot of things, almost everything else attacks the alkene. So maybe I'm trying to draw an enolate. So let's draw, maybe alkene goes there, ketone goes up top. All right, let's zoom in a bit so you can see that. Okay, see what we did? Enolate attacks the Michael acceptor at the beta position, and that shifts the electrons from there to make an enolate. And what does that give us now? I'll abbreviate the structure. pH, ketone, pH. Look at that. Okay, now maybe from ethanol, the enolate just grabs a proton. Oops. Cool. There we go. Now that shows the formation of the 1,5-dicarbonyl product. Okay, 1, 2, 3, 4, 5. That's a Michael reaction, and that is pretty straightforward. Okay. And we're going to move slowly to the Robinson. Okay, the Robinson's going to be like the Michael, but with a little more work. Okay, I like to keep them separate. The Michael is kind of the easy one, and then the Robinson will be the slightly more complicated one. Okay, but there's our Michael. Michael donor, enolize, attacks the Michael acceptor, and then we just grab a proton to make the product. Okay, cool. I'm going to say one more thing. It's really important here. I'm going to mention something that's kind of important. That notice the Michael donor, no, sorry, the Michael acceptor. The Michael acceptor lacks an enolizable CH. It lacks an enolizable CH. That's important. For the simple Michael, the Michael acceptor lacks an enolizable CH. The Michael, so when I say enolizable CH, I mean on the opposite side of the ketone. So we have the alkene on this side, we got the benzene on this side, right? On that position where the benzene is, there's no CH, right? It's a benzene. Let's redraw that nicer. It's a benzene, and there's no enolizable CH right there, right? There's no CH there, it's just a benzene. And so that is critical for this simple Michael. And guess what's going to happen if we have a CH there? That's going to be the crazy one, the Robinson. The Robinson's the Michael plus additional stuff. Okay? So when we have no enolizable CH, we get the simple Michael. And what's the product of a simple Michael? A 1,5-dicarbonyl. Okay? Let's show another example of a simple Michael. So we're on 11, which is what I'm going to call Michael/Robinson. Okay, and let's we're still really talking about the Michael. Let's show another option, another example of preforming the enolate. Preform enolate. So we're going to use a stronger base this time, and it's essentially the same exact thing. So let's do cyclohexanone. I'm going to treat this with a super base. What's a super base? That rips off the proton quantitatively to make an enolate. So there's one base that you should kind of associate with that behavior. Rips off the proton. Super base. What's the super base? 3 letters. LDA. LDA is the super base. We've learned about LDA a bunch of times. LDA is a very strong base. So it's extremely basic. Very good non-nucleophilic base. It's not going to attack the ketone as a nucleophile. It's just a very, very, very good strong base, LDA. Makes an enolate, and which is, you know, these are both the Michael donor. This is the Michael donor reactively. This is kind of like before the Michael donor. But this is going to be the reactive intermediate. If you want to call this Michael donor, you can call that whatever. Okay, we have Michael donor. What do we need to react with now? A Michael acceptor. And what's the requirement of the Michael acceptor for the simple Michael? The requirement for the Michael acceptor for a simple Michael, it's the lack of something, right? The lack of an enolizable CH. So let's use this one this time. Okay, so right, there's a ketone. And what do we not have at the alpha position? An enolizable CH. Those are methyls. There's no CH there, right? So this is the Michael acceptor. Okay, so this is the requirement of a simple Michael. Lack of an enolizable CHs. Okay, what's the product? It's a something something carbonyl, right? A 1, something carbonyl. What's the something? 5. It's a 1,5-dicarbonyl. Okay, so you know there's going to be an H2O step or something here also. It's step 1 is the Michael acceptor, step 2 is water. You can imagine the mechanism of this. And why? What's the mechanism? The enolate attacks. So, and that creates a new enolate, right? One enolate attacks the Michael acceptor, makes a new enolate, and then water destroys the enolate. We get the product. We call it a 1,5-dicarbonyl. Why 1,5? Because it goes 1, 2, 3, 4, 5. You should always do that. Because if you draw a 1,4-dicarbonyl, you screwed up. If you drew a 1,6-dicarbonyl, you screwed up. Okay? Okay, so that's the final product. Another example of a simple Michael. A simple Michael, okay? So let's see here. Okay, and before I do the Robinson, what's the requirement of the simple Michael? Lack of the enolizable CH on the Michael acceptor. So if you do have an enolizable CH on the Michael acceptor, what's going to happen? Just as an example, like there's a simple Michael donor again, MD. Okay, so what's a molecule with an enolizable CH? Okay, that. Okay, now you see in the Michael acceptor, aha, we have a CH there. We have a CH3. We have 3 H's, right? So what we're going to see is that when you do base, like NeOET, this is usually what we use. Yes, it will make the enolizable, sorry, what kind of carbonyl? Michael donor, Michael acceptor. This will make the 1,5-dicarbonyl, But with this CH, the CH3 right there, now more stuff can happen. And this leads to subsequent reactivity. Leads to subsequent reactivity. And what's the name of the other name? Michael and Robinson. So we'll see what the Robinson is next. Okay, so we're cool with the Michael. You got the basic idea of the Michael. What's the product of a Michael? A 1,5-dicarbonyl. What's the product of an aldol? Think back in the aldol. Remember aldols? We're going to need the aldol in a second. But the aldols make alpha beta unsaturated ketones, right? So we learned aldols make things like this. What my point is that when we learn like what kind of product a reaction makes, that's a useful way to learn the reaction. Like I associate a Michael reaction with a 1,5-dicarbonyl. I associate an aldol reaction, which we'll see aldol in a second again. I associate aldol with a what? What's the product of an aldol? The product of an aldol is an alpha beta unsaturated ketone, like this. This is an example of an alpha beta unsaturated ketone. So aldols make things that look like this, or more complicated versions of this. Okay, so that's a useful strategy to learn this. Let's talk about Robinson now. Let's talk about these subsequent steps after a Michael that lead to a Robinson reaction. Yeah, a Robinson annulation is the name. This is a Michael reaction. This is going to be called the Robinson annulation is the word we're using. Robinson annulation. Okay, so now let's talk about the Robinson. Annulation. The Robinson annulation, you might be able to call it like a kind of more complicated Michael. So Michael plus more. Michael plus more. And the Robinson annulation, first of all, what does the Michael create? What's the product of a Michael? The Michael makes a 1,5-dicarbonyl. But with the Robinson, it's going to continue and essentially just do an aldol, but it's a little bit of a process. I actually have a great way to memorize this. So it's 4 steps, A, B, C, D. I strongly recommend you memorize these 4 steps when you're learning the Robinson. Okay, what's the first step of a Robinson? Michael. First step is a Michael. The second step of a Robinson is a proton transfer, PT. PT, and I also like to say re-enolize. Re-enolize. So it's Michael, PT slash re-enolize. Re-enolize. Step C is an aldol. It's going to be, we're coming back to aldol. Remember aldols? Hopefully you haven't forgot the aldol. And it's also intramolecular. It's intramolecular. Intramolecular aldol. It's an intramolecular aldol. Okay? Step D, minus H2O. Remember, what's the last step of every aldol that we've learned? Every aldol we've done, you do the aldol and then you lose water to make the final product, which is an alpha beta unsaturated ketone. Okay, so it's Michael, PT re-enolize, aldol, lose water. Let's show it. I'll try to keep the A and B and C and D going. Here's an example. In this case, I am going to keep the Michael donor on the right this time. MD on the right, Michael acceptor on the left. MA. Okay. There's our Michael donor, our Michael donor on the right, Michael acceptor on the left. Now what's the requirement for Robinson? Is having an enolizable CH on the other side of the alkene. So here we have the alkene, and now we have an enolizable CH, right? There's a CH3 there. There's 3 hydrogens. That's the requirement for Robinson, the easy way I teach this. Okay, the product, we're just using NaOET like crazy in this chapter. It's going to be 2 rings. Okie dokie, there we go. Got a ketone, got an alkene. Alright, not obvious how this all comes together. So we have to step through this whole process. What are our 4 steps again? We're going to do a Michael, proton transfer / re-enolize, aldol condensation, intramolecular aldol, and then the last step of every aldol is loss of water. Okay, so what's the first thing we're going to do? The Michael. So let's do the Michael. How do we do the Michael? So the base, I'm going to take off this proton. You could do it on either side. For this example, I'm just going to take off that proton. It's going to help me. So what's the base do? It takes off the proton to make a what? To making, and this is step A, right? We're doing the Michael right now, right? So it makes an enolate, right? We enolized the ketone. Took the base, ripped off the proton, make an enolate. Now we're going to do the Michael. Okay, so the step A, we could call this the Michael. It's kind of getting, I don't know, whatever. We'll call this part of step A. But the real Michael is next, where the Michael donor attacks the Michael acceptor. Whoops, let's make it a nice enolate. Okay, it's a Michael. That's step A. It's also step A, I guess. We did A twice, I guess. Now we've actually finished the Michael part of this. Maybe I'll go downward a little bit to make sure I don't run out of space. Okay, so we're still A, right? Now, what do we got? The Michael donor part is now a ketone. Yeah. And what's attached to that ketone? It looks like the enolate now attached to the Michael acceptor. So it goes carbon, carbon, okay. You can kind of see how it's a 1,5-dicarbonyl now. It's just in the enolate form here. It goes 1, 2, 3, 4, 5, that right? Because what was the Michael acceptor is now an enolate, right? Cool. So there we are. That's the first step. Michael donor attacked the Michael acceptor. So that's a Michael reaction. But we're not going to stop here. We're going to keep going. And let's go look at the 4-step part. First you do the Michael, then we do proton transfer, re-enolize. So to do this, all I'm going to do is write the letter B. It's proton transfer, re-enolize. And all I'm going to do is assume that the enolate goes from one side to the other side. So the enolate, the orientation of the enolate is going to switch. Carbon, carbon, carbon. Okay, see how the enolate went from one orientation to the other? That's what I meant by PT/re-enolize. Step B was PT/re-enolize, and that's what we just did. We just moved the enolate from one side to the other. Okay? PT re-enolize is step B. PT re-enolize. Okay? So we got a new enolate. Alright. And what do we know about enolates and their reactivity? Nucleophiles or electrophiles? It's a nucleophile. Whoa, look, check it out. We have a nucleophilic enolate and an electrophilic ketone now. What was the Michael donor and a nucleophile is now ready to be an electrophile. Enolate is going to attack the ketone. The nucleophilic enolate is going to attack the electrophilic ketone. And what step is that? Let's go back to our... Now we're in step C, intramolecular aldol. So we're ready for our intramolecular aldol. So, well, what's the mechanism of it? Enolate attacks ketone. Okay? Enolate attacks ketone. Alright, and now I'm going to, remember what when we did aldols, we mentioned the name of the intermediate in an aldol. We actually, we called it a what? A something hydroxy ketone. Is it an alpha hydroxy ketone or a beta hydroxy ketone? Ah, it's a beta hydroxy ketone. So the product of an aldol is a beta hydroxy ketone. Beta hydroxy ketone. Okay? That was, what step was that? We did A, Michael. We did the proton transfer re-enolase. What was this? Step C. What's the name of step C again? The aldol. Step C is the aldol. The intramolecular aldol. So we did an intramolecular aldol to make a beta hydroxy ketone. And what's step D? And what is the final step of every aldol? Loss of water, dehydration. Okay? I am not going to review that one. C aldols. For the mechanism part of that. I stepped through this all. But the dehydration is not that exciting. It's simply we enolize the ketone. We enolize the ketone, and then the enolate swings back and kicks off the OH. That's what it was. Not that exciting. Most likely, if I give this on a quiz, I'm not going to have you worry about that. But you should know that. You should know that reaction. Go look at the aldol section. It's not difficult. I just don't have space, right? So the last step of this, under basic conditions, which we have base, the base takes the proton and re-enolizes, so form an enolate here. Then the enolate swings back and kicks off the OH. And what's your final product? What's the name of this? A cyclic something something ketone. A cyclic alpha beta unsaturated ketone. A cyclic alpha beta unsaturated ketone. Yeah? Alright. I'm going to do one last example, and I think we're ready then for the next chapter, the PowerPoint. Okay, so let's see. Well, actually, let's step through this one more time, the Robinson, while we have it all done. What's the Robinson? It's a four-step process of what, and what. Michael, proton transfer re-enolize, aldol intramolecular, loss of water. How do we do this? And the other thing is, it's very hard. I can't just like say, oh, this is the Robinson product. That's why you have to step through this. If I give you these two pieces, you would have to step through it to figure out the product. There's no magic way to just say, oh, they come together and they make this, okay? What was the requirement of a Robinson? Why did it not just do a Michael and only a Michael? Remember the big thing was that this has a enolizable CH, right? The Michael acceptor has an enolizable CH, and that's what allows the Robinson to proceed. So what's step A? Step A was Michael, essentially. Base takes proton, makes an enolate. Enolate attacks the alpha beta unsaturated ketone. Yeah? And now we have essentially the Michael product, but as an enolate form. And it's a 1,5-dicarbonyl with one of the carbonyls being an enolate. 1, 2, 3, 4, 5. Alright, so that's your 1,5-dicarbonyl. And then what was step B? Is PT re-enolize. All I do is I just imagine where the enolate is and switch it to the other side. Okay? And then the intramolecular aldol now, enolate attacks the ketone, electrons go onto the oxygen. I am skipping the protonation step. It's happening, but we're just showing the key intermediates. We're not doing a very detailed mechanism here. And yeah, I mean, you should be able to draw it. Most likely on a quiz, I would just say, hey, draw all the intermediates and the final product. Okay? All right, and this is a beta hydroxyketone product of the aldol. And with base, you lose the water and you make that final product. Okay, that's the Robinson. And what do you need to memorize? I think the 4 steps. If you put them in an index card and an example, that might be all you need. Okay. So let's try doing this backwards. Let's do a synthesis. Synthesize by Robinson. Let's just try. This is actually a homework problem. I think it's, I don't know the problem number, but it's a nice example. Let's say we got this guy. And we need to make it via the Robinson. This is a synthesis product. And we want to go backwards. Okay, so let's make this by the Robinson reaction. Let's make this by the Robinson reaction. Okay, so these kind of arrows are called retrosynthesis arrows. It's like a double arrow. And what that basically means, it's the same as going backwards. It's like I could draw this kind of arrow and say, hey, we're making this. Like this is the final product. Let's draw the precursor. Or I can do this. It's called a retrosynthesis arrow. Okay. So if we're making this from a 4-step process, and this is a cyclic alpha beta unsaturated ketone. And that's the product of a Robinson. Okay, if we're doing a 4-step process, A, B, C, and D, what's the last step? It's D. And what was the last step? The last step was dehydration of a beta hydroxy ketone to make the alpha beta unsaturated ketone. So I can envision now this not be an alkene, but maybe a hydroxy at the beta position. So let's draw that. Okay, so methyl will get a ketone. Alright, and now where's the hydroxy? In a aldol, the hydroxy is at the alpha or beta? It's at the beta, right? Okay. Okay, so that would be step D, would be the dehydration of this. So we're going backwards, right? This is the final product. This is right before that. It's a beta hydroxy ketone. And now, what's step C? What was step C? It was the intramolecular aldol. Okay. And so I can envision the bond is going to be between the alpha and the beta carbons that makes the aldol. So there's the bond that makes is made by the intramolecular aldol, which is step C. Okay, that's something to remember. Is what bond is created in step C? It's the bond between the alpha and the beta in the final product. Okay, because the step C creates the alpha beta bond that we see in the final product. So so what's this going to look like now? enolate here. And a ketone there. Aha. Okay, so this, if we were going in the forward direction, of course you can envision now this would swing and this would attack. Right, that's the enolate, that's the aldol, right? We're going backwards, but in the forward direction, the aldol would be O- attacks and makes the ring, right? Okay, let's see, for space, let's zoom out a bit. Okay, we're going backwards from D, C, what's next? Going backwards, DC, B, what's B? Remember B? PT slash re-enolize. And so now we just envision this. I'm gonna, yeah, we can see it. Where's the enolate gonna be? We're going backwards. So maybe I'll draw it this way. I'm trying to have you see everything. So let's go this way. There's B. All right. B is the PT re-enolize step. So it's going to look exactly the same. Ketone, ketone. Everything's the same. Right? Even the O- is the same. What's the difference between this molecule and this molecule? Because what was B? It was PT re-enolize. So the enolate was on this side, now the enolate's on this side. Okay, so we're almost done. D, C, B, and now you can see the enolate there. And we're stepping backwards. We did D, which was the dehydration, C, which was the intramolecular aldol, right? Going backwards. B was the PT re-enolize, and what was step A? And I'm going to go up this way just because of space issues. A in the Robinson was the Michael, and this now is going to be the disconnection of these two pieces. So it's going to be between the alpha of the Michael donor. This is going to be the Michael donor on the right, and then this will be it'll be between the alpha of the Michael donor and it'll be the other carbon, which will be the Michael acceptor. So this is the disconnection now. So let's see. Can we imagine what it's going to look like? It's going to be that, right? That's going to be the Michael donor. Now we can see that. All right. And what's the Michael acceptor going to look like? That might be harder for you to see. How many carbons is it going to be? Well, there it is. That's going to be what's the Michael acceptor. How many carbons is that? That's 1, 2, 3, 4, 5, right? It's 1, 2, 3, 4, 5. It's a 5-carbon thing. That'll be where the alkene is. That'll be where the ketone is. Right? Alkene will be there. Ketone will be there. And there'll be 2 more carbons. That's 1, 2, 3, 4, 5. So it's going to be, there we go. That's A. So that was pretty fun, huh? We did the Robinson backwards. Let's step through it again real quick. So the Robinson was going backwards. First was step D, which is the dehydration, and that's how we figure out, oh, that's the, it's the beta hydroxy ketone. Yeah. Then we envision the intramolecular aldol. So we break the bond. That bond will be broken going backwards. To make this enolate would attack that ketone to give this beta hydroxy ketone. Now we go to B, which is the step B, which is the re-enolization step. So you just imagine the enolate go to the opposite side, and then we just envision the Michael going backwards. Figure out where the squiggly is. So it's pretty clear where the Michael donor part is going to be here. And the Michael acceptor part will be the thing that's the enolate. and that gives us these two starting materials. These two as a Robinson will give this final product. That's pretty cool. Here's a full view of it all. I would recommend step through this whole process yourself. See if you can get through this. Apply those DC, B, and A steps backwards. Okay? You need to know this going forwards, you need to know this going backwards. That's the Robinson. Okay, so yeah, I thought that we would have time to get into the next chapter, but it looks like we're out of time. I'm sure you guys are so bummed and excited to move on to chapter, I think it is 19. But we will do that next time. Okay? See you at the iLearn site for how the quizzes are going to be structured and what material will be on the quizzes. And that's the kind of the authoritative source for what's on the quizzes. And you can obviously always email me if you're a little confused by that. Okay, thanks. Have a good weekend.